Hello, you're welcome. All right, so now we are here, okay? We're gonna be studying capacitors and of course dielectrics. Okay, now what are capacitors, okay? Now a capacitor is a device that stores charge in an electric field, okay? So devices that stores charge in an electric field. Now we've already treated electrostatics, okay? We said that static electricity that is being generated by a static charge. So there are some devices that have the ability of storing these static charges in an electric field, and one of them is capacitor. All right, a capacitor. Now a capacitor is made up of two metallic plates separated by a dielectric medium, as shown in the diagram below. I don't know whether this diagram is actually showing well, but I could actually draw. Okay, so invariably a capacitor, okay, is just gonna be okay, two metallic plates, right? So I should use this, okay, positive plate and negative plate. All right, then of course it has having a terminal, okay, a terminal is being connected from it. Now, in between the two plates, okay, lies a medium, okay, an insulator is found in between the two plates. And of course, this insulator is what is known as a dielectric medium, okay. That is where you have the reservoir where the charges are being stored, okay. So one part of the plate can be called the positive plate. The other part is negative, right? Negative plate. All right, so have the positive terminal and the negative terminal, okay. So I hope that is well understood. So a capacitor, what this capacitor does is that it actually stores, okay, it stores electric charge. It stores electric charges. All right, so now let's proceed. Okay, having known that, all right, so now let's study talk about the charge that is stored by a capacitor. Okay, now when do capacitors store charge? When a direct current is supplied to a capacitor, okay, it stores charge Q, which is directly proportional to the potential difference of voltage supplied to it. So now, which simply means, okay, simply means that, okay, this capacitor now doesn't just store charge, right? It doesn't just store charge. It stores charge in an electric field. That which simply means that how do I create the electric field? I must I need to supply this capacitor with, okay, a potential difference, okay, from a direct current, right? A direct current source, which of course is here a battery or a cell, okay. So when I supply a potential different V to this capacitor, of course current flows through it, flows through the capacitor. As this current flows through the capacitor, it actually store charge, want some quantity of charge Q. All right, now it is shown that the quantity of charge that it will store depend on the voltage that is being supplied. All right, they are proportional. The more voltage you supply, the more charge. So that means the charge stored by capacitor Q, okay, is directly proportional to the voltage that are supplied to the capacitor. And of course, you know very well that okay, uh if I should now bring equal to, I will now have to bring a constant. Okay, now this time around the constant is C. All right, so which simply means that the quantity of charge that a capacitor can store, all right, depend on two things. C is the product of C and V. So what are these parameters? Okay, all right, so now let's write them down. This the V, okay, let me start with the Q. Okay, the Q is of course is the quantity of charge. quantity of charge. Okay, then of course the V is actually the voltage supply, or okay, or we call it potential difference. Potential difference, okay, supplied by that by the capacitor. Then now C now becomes a constant, all right? That actually depend on it's a constant depending on the capacitor, right? That constant is what is known as the capacitance. Okay, capacitance of a capacitor. The capacitance, all right? So the amount of charge stored depend on this, okay? Charge stored depend on the voltage and the capacitance. And the question is, what is capacitance, all right? How can we define capacitance? Now, from the formula, which we know that, okay, quantity of charge stored is equal to quantity of charge stored is equal to, okay, CV. So the capacitance now, if I should make it the subject of formula, all right, C is going to be equal to Q, right? So the capacitance of capacitor from this formula now we can define it as the measure or the quantity of charge, okay, a capacitor could actually store per unit voltage. Charge a capacitor can store per unit voltage, right? Now the charge a capacitor stores per unit voltage varies depending on the capacitance, right? So now, and this capacitance of a capacitor is actually being measured by the unit, okay? The unit is measured in farad, okay? F by symbol, right? So which simply means that if I actually get to buy capacitor, okay, I want to store charge, right? I discovered that the charge that 20 microfarad capacitor will store is different from the charge 30 microfarad will store when I apply the same voltage, all right? So 30 microfarad, all right, will store more charge than 20 microfarad, even though it is the same voltage that is applied to that capacitor. So please take note. So the SI unit of capacitance is actually in farad. So I hope that is well understood. Let's proceed. Okay, so capacitance of a capacitor, we've actually defined that. All right, so now let's look at capacitors connection. Capacitors connected in parallel and capacitors connected in series. Okay, sometimes you need more than one capacitor, right? Sometimes you need more than one capacitor. Now we're going to look at that. The symbol of a capacitor, electrical symbol, all right? Of course, a capacitor is an electrical component, all right? The electrical symbol of a capacitor is just okay, two small parallel line, all right? Equal parallel line. Let me draw that very well, okay? Two small equal parallel line. So this is how we, then of course you now connect the terminal. So this symbol is used to, okay, to represent, all right, a capacitor. See, once you see this electrical symbol, that's a capacitor. So now we're looking at this capacitor being connected in parallel. Okay, so let's say three of it. So I'm going to duplicate this into three, right? Three, and then I'll connect it in parallel. Okay, one, two, then three. Okay, so they are now join it in parallel. Now, of course, this is parallel connection. When you join positive end to positive end, negative end of the capacitor to negative end, this is parallel connection. Okay, so you can now supply them, okay, with voltage. Okay, let's say this terminal, okay, with common voltage VAB. Now let me call, let's say this capacitor is C1, this is C2, and this is C3. All right. Okay, so now one thing about the characteristics of capacitors when you actually join them in parallel, okay, as shown like this, is the fact that, okay, when the current actually when the current from the voltage supply enters the capacitor, the current actually divides. Okay, some current enters into C1, some entered into C2, some enter into C3. So that simply means that they will store different charges. The charges stored by them will actually will vary. Okay, C1 will store different charge, C2 will store different charge. Okay, so I don't really okay, like I can still go I can still prove the formula. Okay, so they store different charge, so that means their charges varies. Okay, so the total charge they will store, right, or the capacitor will store, is going to be equal to the sum of the charge that is stored by capacitor 1, I call it Q1, plus the charge that is stored by capacitor 2, I call it Q2, then plus the charge stored by capacitor 3, I call that Q3. All right, so now, but their voltage will be the same. Since they're connected in parallel, the voltage across all of them will be the same. What will only vary is the charge they will store. All right, having known that, okay, from our formula that charge store, okay, pardon me. Okay, so having known that charge store by capacitor is given as CV, right? So that means for this, I'm gonna have C total multiplied by the voltage. For Q1, I'm gonna have C1 multiplied by voltage. For C2, I'm gonna have C2 multiplied by voltage. For C3 multiplied by voltage, and of course, you know, the voltage is the same. Since the voltage are all the same, okay, I'm using V. So now, so I'm gonna have CT multiplied by V. So voltage is common here. I'm gonna factorize. I take the voltage out, then I write the other factors, which of course is C1 plus C2, then plus C3. All right, so V cancels V since they are found the same, okay, at both sides of the equation. So now I have that the total capacitance when capacitors are connected in parallel is going to be their sum, C1 plus C2 plus C3. Okay, so we simply, if I had to bring let's say 2 microfarad of capacitor, all right, then 3 microfarad capacitor and possibly 5 microfarad capacitor. All right, if this connection, if I connect them in parallel, the total capacitance I'm gonna have is gonna be 2 plus 3 then plus 5. All right, so that is how we capacitors are being connected in parallel. All right, and that's what you get as the total capacitance. All right, so now what about series connection? Okay, so I'm gonna look at series connection. Okay, right. Okay, so let's join them up. Pardon me. All right, so join them up. Okay, so this is series C1, 3 capacitor C1, C2, C3. This is series connection. So I can now supply voltage, okay, across the network. Okay, so this is voltage supply V. Now current flows, okay. Now I discovered that one thing is sure, since all of them are in series, the same current passes through them, and because of that, they'll store the same amount of charge. When capacitors are connected in series, they will definitely store the same amount of charge. All right, but what will actually vary is the voltage across them. Voltage across C1 will be V1. Voltage across C2 will be V2. All right, So the voltage across C3, okay, will be V3. So they will share the voltage supplied to them, okay, differently. They will have different share of this voltage that is supplied to them. So the voltage that's supplied to them, okay, is going to be shared among them. That's going to be V1, okay, plus V2, then plus V3. All right, so from Q being equal to CV, so we can simply, of course, making V the subject of formula, we know that V is going to be equal to Q all over C, right? So here we go. So V here, I'm going to have Q all over C equal to, okay, so this is V total. The V supply is the total V, so that's going to be C total. V1 now going to be Q is the same, okay, mind you, was C1, then now V2 Q all over C2, V3 is Q all over C3. Okay, so now what do we do? So Q all over CT is going to be equal to Q is common, I have to factorize. So I'm having 1 all over C1 plus 1 all over C2 plus 1 all over C3. So Q being a common factor, both sides of the equation cancels out. So I'm left with 1 all over C, total C, okay, is going to be 1 all over C1 plus 1 all over C2, then plus 1 all over C3. Okay, so now this is what you have as total capacitance, okay, when capacitors are actually connected in series. So the reciprocal of their total capacitance is going to be the sum of the reciprocal of their individual individual capacitors, right? Capacitors. For example, now if I still have that same question I gave you before, uh, of 2 microfarad, okay, comma 3 microfarad, comma 5 microfarad, all of this being connected in series, pardon me. So what I'm going to have is 1 all over CT, okay, since it's series connection, that's going to be 1 all over 2 plus 1 all over 3, excuse me, then plus 1 all over 5. Okay, so the LCM that we actually go for this, okay, so the LCM available is 30, all right, so 1 all over CT is going to be equal to 30 divided by 2, that's 15. 15 times 1 is 15. Then, of course, plus 30 divided by 3, that's 10. 10 times 1 is 10. 30 divided by 5, that's 6. 6 times 1 is 6, okay? So, adding up, there's going to be 25 plus 6, right? 31. 31 all over 30. But that's not the answer, because what you're looking for is a CT, not 1 all over CT. So, you have to invert the fraction, okay? So, CT now becomes 30 divided by 31. So I hope that is well understood. All right, so let's proceed. Okay, back to our slide. So So in this case now I have a 100 microfarad, 20 microfarad, 50 microfarad. How do you get the total? That's gonna be 1 over 100 plus 1 over 20 plus 1 over 15. Okay, still. So now here we're going to talk about, but before then, okay, I could actually there are more complex examples that you will encounter in exam. Okay, apart from a network, right? Capacitor being okay, capacitor connected in series or parallel being given, okay, as a question for you to resolve. You can also be given the combination of the two, which is series parallel. For example, okay, you might be asked to, okay, to evaluate the total capacitors, the total capacitors. All right, of the network below, of the networks below. Okay, so now let's look at some example. Let's say I've been given this. Okay, sometimes you might be given some complex network, okay, that involve both series and parallel at the same time. Then okay, so let's say this is 2 microfarad, 2 microfarad, 2 microfarad, 2 microfarad, all right? And let's say this is 1 microfarad. This A, let me look at another one, or B. Okay, so let's say you are given this. Two microfarad, 2 microfarad, 1 microfarad, 1 microfarad. Okay, so let's say you have been given this to evaluate. Okay, so let's solve this. Let me start with the A part of the question. Solution. So how do I resolve this? This is series parallel. So first of all, I have to look at the fact. I have to look from this circuit. I know that 2 microfarad. This and this. Okay, are in series. This and this are in series. Okay, I have to resolve it. After resolving it, then all of them. Okay, the two series, okay, found at the upper part and lower part are now in parallel. So first of all, you have to resolve this series. Okay, so resolving this series, 2 microfarad, 2 microfarad, 2 microfarad. All right, once you resolve it, you will have a single capacitor up here and a single capacitor down here, which of course is in parallel. So now I want to resolve the two. So let me call that C1 as my first resolution. Now remember, if I want to resolve a series, all right, that's 1 over C1. Okay, I'm using C1 now. It's gonna be the total. There is the total capacitance of this series up here, right? So I'm calling C1. So I'll say 1 over C1 is gonna be equal to, okay, 1 all over 2 plus 1 all over 2. Remember, series resolution. Okay, so now I'm gonna give you a very a shortcut, right, for me to find C1 without going through the process of finding LCM. Okay, and it's this shortcut is basically for when the capacitors are just two in series. Okay, two series capacitors, right? So the formula is the product of the capacitor divided by the sum. Okay, so C1 is gonna be product, that's two, the two capacitors, two, that's 2 times 2, and divided by their sum, which is 2 plus 2. 2 times 2 is 4. 2 plus 2 is also 4. So that means C1 is 2 microfarad. Oh, sorry, 4. Please pardon me. Okay. 2 plus 2 is also 4. So that should give me 4 divided by 4. That's 1 microfarad. Okay. 4 divided by 4, 1 microfarad. So now, so that simply means that C1 now being this, so this one too, the capacitors, these two capacitors, okay, at the lower part of the circuit is also 1 microfarad. All right, so I still need to submit, so I call that one C2, 1 microfarad. So now let's now resolve the two. Now both 1 microfarad and 1 microfarad, okay, are now in parallel. All right, so let me call that C3. So now C3, now remember in parallel, C3 is gonna be C1, okay, plus C2. So 1 plus 1, that's 2 microfarad. So now that is that has resolved the whole of this network, the whole of this. All right, then now it is now connected in series with 1 microfarad. Okay, so so now total now can now say, okay, C total is going to be equal to the series connection of both 1 microfarad and of course 2 microfarad. Now since they are series, remember I will apply the product all over sum. Okay, so that's gonna be product 2 times 1 divided by sum 2 plus 1, which of course is 2 all over 3 microfarad. Okay, so we can actually evaluate that. Okay, so that is for the A part of the question. Now the B part, let's do justice to it. Okay, so let me clean up. Okay, so here we go. So let's now look at this. Of course, this we know very well they're in parallel. So you gotta resolve it. Okay. So I call that C1. Okay, parallel. Of course, that's gonna be 1 plus 1, which gives 2 microfarad. So now after resolving this, now everything now is in series. Okay, both this 1 microfarad C1 plus, okay, plus this, they're all in series. Now is series, so we can now get the total of 1 over C T total. Remember series connection. Okay, that's going to be 1 over C1 plus 1 over C2 plus 1 over C3. So of course, since I've already used C1, okay, C1 is 2 microfarad. That's going to be 1 over 2 microfarad. Okay, plus 1 over 2 plus 1 over 2 plus 1 over 2. All right, LCM is what I'm gonna apply here now, not product all over sum. Please, product all over sum is just for 2 capacitors, right? So LCM here is 2. 2 divided by 2 is 1. 1 times 1 is 1. Okay, the same. the same also. So that's going to be 3 all over 2, right? So now don't forget that for me to now find the CT, I have to invert C total. I have to invert. That's going to be 2 all over 3. Okay, so microfarad. So I hope that is well understood. Okay, we will solve question. Okay, don't bother, we'll solve, definitely solve examination question in one of these videos. Okay, so here we go. We proceed with our slides. So now we're gonna be looking at the energy stored by a capacitor. Okay, so there's gonna be I think the last subtopic. Now the energy stored by a capacitor in electric field is giving us half of the charge, okay, stored multiplied by the voltage. So if you have to evaluate energy stored, okay, so let's say the energy of a capacitor, the energy that a capacitor stores in electric field is, okay, evaluated by actually, okay, by the formula, half of the charge, total charge stored by the capacitor or the capacitors, they multiplied by the voltage, the potential difference applied. Okay, so this is one formula, right? You can use this to evaluate energy stored by capacitors in electric field. Now, having known that Q, okay, is equal to CV, so the energy also stored by the capacitor can also be given as half of Q, which we know is CV, okay, then of course multiply by V again, right, times V. Q is CV, so CV times V, that's gonna give half CV square. All right, that's still another way, okay. In this case, let's say making V the subject. Of course, if you're making V the subject, V is equal to Q all of us see, right? So half of QV, okay. If this time around I'm actually a substitute for V, right, I'm gonna have half of Q, right, times V, which of course is Q all over C. So the energy now becomes half Q square divided by C. Okay, so that is it. Energy stored by a capacitor, that is the formula you use. All right, okay, so we are going to solve the examination question in the next video. See you in the next video. Thank you very much.